Hey everyone, welcome to Mission Science Workshop. I'm here with my co-host Jeff, and today we're going to be talking all about earthquakes and earthquake-safe buildings.
Earthquakes and earthquake-safe buildings. Before we get started, I have a few questions I'd like to ask. How you answer those questions depends on how you're watching this video. If you're watching the video in a classroom or with your classmates, you can pause the video and take turns answering some of these questions. If you're watching the video alone, you can write down the answers to the questions in your notebook. What are some things you already know about earthquakes? Have you ever felt an earthquake? What did it feel like? Do we have a lot of earthquakes here in San Francisco? Why do we build such tall buildings here in San Francisco when we have so many earthquakes? What kind of forces, pushes or pulls, are acting on buildings before an earthquake and during an earthquake? How do engineers make those tall buildings safe during earthquakes? Hopefully, you've had some time to answer these questions either in your notebook or as a class. Let's get started. When you're walking around San Francisco, it's easy to think that the ground underneath you isn't moving, but it is. Today, we're floating on giant islands of rock. Those islands float on a sea of liquid magma. We're standing on the crust. That crust isn't very deep. In fact, if you shrunk the Earth down to the size of an apple, the crust would only be as thick as the peel. We call these giant islands of rocks tectonic plates. Here in San Francisco, we really have to worry about two of the plates. First one is the biggest plate of them all. That's the one known as the Pacific Plate. We're standing on the North American Plate, and the Pacific Plate is crashing into the North American Plate. Here in San Francisco, they're grinding past each other in a place known as the San Andreas Fault. As these plates grind past each other, the friction of their collision builds up tremendous amounts of pressure in the rock underneath the surface. When that pressure becomes too great, the rock fractures, releasing tremendous amounts of energy in the form of seismic waves. We feel those waves as earthquakes. In San Francisco, we have several faults that run right next to each other. The Hayward Fault, the San Andreas Fault, and several other smaller faults also dot the Bay Area. Those faults have been responsible for two major earthquakes in the past 100 years. The 1906 quake, which registered 7.9 magnitude and destroyed 80% of the buildings, mostly to fire. 300,000 people went homeless, and over 3,000 people died. In 1989, there was another quake, registering 6.9 on the Richter scale. Collapsed portions of the Bay Bridge and killed over 60 people. We've learned a thing or two about buildings in San Francisco. 1906 taught us how to shut off gas lines so that we prevented fire, and the 1989 quake taught us how to build bridges a little bit better. If San Francisco is located in the area where two tectonic plates meet, and there are several fault lines underneath our feet, why is it that we continue to build taller and taller buildings? Well, we learned a lot from the 1989 earthquake, including the fact that there are nearly 40 buildings that have flawed construction techniques that could lend themselves to collapse. These buildings include such iconic staples of the skyline as the Transamerica Pyramid, the PG&E building, Google's headquarters, and a smattering of others. On top of that, they're built on landfill pushed into the bay from the 1906 earthquake. So how is it that we can build tall structures like the Salesforce Tower? Well, luckily, we've learned a lot about building buildings since 1989. Most new high-rise construction since then has incorporated a technique known as base isolation. You can see it here, where it allows the tower to move independently of the ground shaking beneath it. Here are a few of the most common earthquake-resistant construction techniques. You've already heard a little bit about base isolators. Those allow the building to move independently from the ground shaking around it. We also use X or triangular shaped support structures because triangles are some of the strongest shapes in nature. Buildings with wide bases allow for less shaking to reach their tops because their bases are so well supported. You'll see some of these construction techniques in action in the next activity, as well as get a chance to try them out when you try to build your own tower.
For this next activity, we're going to simulate what it's like to be a building during an earthquake. Now, there are two different types of shaking that happen in an earthquake. There is the horizontal shaking, kind that makes you go back and forth like this and makes you feel like you're tripping over your own feet. And there's a vertical shaking, which kind of feels like a big wave, like you're on a roller coaster and you're going up and down and up and down, like the bottom of the floor is falling out from under you, because it kind of is. Now that second force is really hard to replicate here in the workshop. I can't move the ground up and down, but we can replicate that horizontal force. And we're going to do that by pushing off of a really solid object, like a wall or a really heavy desk. Now remember, a force can be either a push or a pull. For this activity, we're going to be doing a push. Now, first things first, you got to remember that this is a moving activity. So we want to make sure that the area around you is totally clear of objects so that you don't run into them and you don't trip over. My assistant Jeff over there is standing a socially distant 6 feet away, so he should be fine. Now, the first building design that we're going to test out with your body is a really, really tall tower. Now, in order to do that, we're going to ask you to stand on 1 foot. Do you feel stable right now already? Maybe some of you are really good at keeping your balance. Well, now imagine that you're in an earthquake. So what we're going to do is when you're standing on 1 foot, you're going to put one hand against that wall, and when we count down from 3, when you get to 0, you're going to push off that wall. Now that push is you putting some force into that wall, and that wall pushing you right back. So hopefully, you're going to move a little. All right, let's stand on 1 leg. Count down from 3. 3, 2, 1, push. Whoa. Did you go really far? Were you really a stable building to begin with? Well, let's try to add a little bit more stability to the building. That's you. This time, we're going to have you stand with 2 feet together. Let's try it again. Count down from 3. 3, 2, 1. Whoa. Got a little close to Jeff there. Good thing he doesn't have any lungs. All right. Did you move as much? Probably not. Let's try it again by adding a little bit more stability. So for this try, I'm going to have you stand like I'm standing now, with your feet directly below your shoulders. You should be able to draw a straight line down from your shoulders to your feet. You ready? 3, 2, 1. Did you go as far? Probably not. Let's try it one more time. This time, we're going to stand with our feet really far apart. Now, you don't have to do the splits for this activity. The best trick that I can tell you is to put your hands on your hips and put your feet below your elbows. So draw a line from your elbow down to your feet. Draw a line from your elbow down to your feet. That's where your feet should be. All right. One more time. 3, 2, 1. Did you move at all? Maybe the top half of you did, but your feet probably didn't move. Take a look at the shape being made by your legs. That shape is a really, really stable shape. And we're going to remember it later when it comes time to build.
All right, for this last activity, you're going to get a chance to build your very own tower and see if that tower can withstand the forces that act on buildings during an earthquake. Now, in order to do this activity, you're going to need some materials that you can probably find lying around your house. The first thing you're going to need is some cardboard. A big piece of cardboard. If you don't have a big piece of cardboard, you can always take 2 pieces of cardboard and tape them together. And if you don't have cardboard at all, you can use a cutting board. Now, the thing that you're actually going to be building the tower out of is spaghetti. Spaghetti. No, can't eat in the workshop. If you don't have any spaghetti, you can also use some straws or some bamboo skewers. If you don't have any of those things, you can use pencils, markers, or pens. Now, the thing that you're going to use to hold your tower together is some tape. Now, I prefer masking tape because it's easy to tear, but you can also use Scotch tape. Now, I have a tower that I can show you as a demonstration so you can see how tall you should try to get it, and we're going to show you how long 10 seconds is when you actually try to shake it for it. All right, are you ready for some magical editing through the filmmaking process? All right, here's my tower. You can see it's pretty tall. It's about 1.5 feet tall. Now, it is not very stable. Have I used some of those things that we talked about earlier? Does it have a really wide base? Are there a lot of triangles involved? Well, let's see just how long this thing can withstand its shaking. Remember, we have to shake it for 10 whole seconds. Doesn't seem like a lot, but trust me, when you're watching your tower fall over, 10 seconds can feel like an eternity. Are you ready? Let's count down. 3, 2, 1. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Well, it's kind of still standing. Yeah. This thing fell over. The only reason it's still in one piece is probably because I used so much tape. But if this was a real building, well, let's just say I wouldn't want to be in it. Now, you're going to get a chance to build your own. Remember, learn from my mistakes. I didn't have a lot of triangles in there. My base wasn't very wide. See if you can build something that will withstand shaking for 10 whole seconds. One thing you can also do, I attached my tower to the base. Now, that keeps it from moving around as much all over, but maybe it makes it a little bit more unstable. So if you want to attach it, that's your choice. If you don't, let's see how that works too. You get to be the engineers and learn from your mistakes. I'll catch you back once you've finished your towers. All right, hopefully you've had a chance to finish your towers. Hopefully they're looking pretty sweet and are really, really tall. Well, now we're all going to shake them together. And we're going to see just how many of our towers stand up. Now, I've brought out and made another tower, and we're going to bring it out now and see if this one stands up for as much shaking as the last one did. Really, if it stands up at all, that's a win. All right, here's my new tower. Now you can see this one is mostly triangles. Kind of like a big pyramid on top of another pyramid. Now, you'll also notice I haven't attached it to the base. Now that means that it kind of slides around a little bit like that, but maybe that'll help keep it in one piece. Are you ready? All right, we're going to shake it for 10 whole seconds. Some of you might want to say goodbye to your towers right now. All right, you ready? 3, 2, 1. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ha ha! Still in one piece. But it was sliding all over there. Did yours stand up? That's great if it did. If it didn't, that's okay too. Hopefully you've learned something by failing. Now, you get a chance to try to redesign these because I have 2 more challenges for you. We only shook these for 10 seconds. Now, 10 seconds isn't very long, but as I said, it probably felt like a long time while you were watching your tower shake. The 1989 Loma Prieta earthquake, the shaking lasted for 30 seconds. So my first challenge to you is to see if you can get your towers to last for 30 seconds. And if you can build your towers to last for 30 seconds, my second challenge to you is to get it to last 60 seconds. Because that's how long the shaking lasted for in the 1906 earthquake. So, if yours didn't make it through 10 seconds, you can redesign and rebuild because that's what engineers do. They learn from their mistakes and they build bigger and better the next time. If yours did last for 10 seconds, you can go right on to the 30-second challenge. And if you get it to last for 30 seconds, you can go right on to the 60-second challenge. All right, y'all. I've had a lot of fun. I hope you do too. And I hope to see you back at the workshop soon. I know Jeff over there misses y'all a lot. Stay safe, and from all of us at Mission Science Workshop, keep looking up.